Hey everyone and welcome. Today we're tackling a Leetcode hard problem called sum of k mirror numbers. It sounds a bit complex with all the mirror and base k talk, but don't worry, we're going to break it down step by step and find an elegant solution together. Ready? Let's get started. Alright, let's look at the problem statement. The main goal is to find the sum of the first n numbers that are special. They call them k mirror numbers. What does that mean? Well, a number is a k mirror number if it reads the same forwards and backwards in two different numeral systems. First, it has to be a regular palindrome, in base 10. And second, its representation in some other base, let's call it base k mirror creen, also has to be a palindrome. We're given the base k and the counteen, and we need to return the sum. So let's make this crystal clear. A k mirror number has to pass two tests. First, is it a palindrome in base 10, the way we normally write numbers? For example, the number 9 is a palindrome. So is 121. Second, we convert that same number into the given base k perds, and we check if that new string of digits is also a palindrome. The example shows that for a k value of 2, the number 9 works perfectly. In base 10 it's 9, which is symmetric. When we convert it to base 2, we get 1001, which also reads the same forwards and backwards. So 9 is a perfect two-mirror number. Let's walk through an example. Suppose we're given k equals 2 and n equals 5. Our job is to find the 5 smallest numbers that are palindromes in both base 10 and base 2, and then add them up. How would we even start? Well, we could just start checking numbers one by one. Let's try it. Number 1. In base 10, it's a palindrome. In base 2, it's also just 1, which is a palindrome. Great. That's our first number. How about 2? In base 10, it's a palindrome. But in base 2, it's 10. That's not a palindrome. So 2 is out. Okay, let's try 3. In base 10, it's a palindrome. In base 2, it's 11. Hey, that's a palindrome too, so 3 is our second number. If we keep doing this, we'll eventually find that 1, 3, 5, 7, and 9 are our 5 smallest two-mirror numbers. Adding them up gives us 25. That little exercise of checking 1, 2, 3, that's the brute force approach. And it works for small examples, but it has a massive problem. The k-mirror numbers get very spread out very quickly. As the slide says, if we needed to find 30 of them, the last one is a gigantic number in the billions. Trying to loop from 1 all the way up to 8 billion would take, well, way too long. Our program would time out for sure. We need a much smarter way to search. So what's the smarter way? Instead of checking every single number, let's flip the logic. Why waste time on numbers like 12, 13, or 14, which we know aren't even palindromes in base 10 to begin with? The aha moment here is to only generate numbers that already pass our first test. Let's create a machine that only spits out base 10 palindromes, like 1, 2, 9, then 11, 22, and so on. Then, we only have to run our second test on these candidates. This is way more efficient because we're skipping all the junk in between. Okay, but how do we build this palindrome generating machine? It's actually pretty clever. We can construct any palindrome from a smaller root number. Let's take the number 12 as our root. To make an odd-length palindrome, we take the root, which is 1, 2, and then we append the reverse of the root, except for its last digit. So the reverse of 1, 2 is 2, 1. We drop the last digit, 2, which leaves us with just 1. We stick that on the end to get 1, 2, 1. For an even-length palindrome, it's even simpler. We just take the root, 1, 2, and append its full reverse, which is 2, 1. That gives us 1, 2, 2, 1. If we do this for every increasing root number, 1, 2, 3, and so on, we can generate every single base 10 palindrome systematically. Alright, here is the complete Python code that puts this all together. I know, it might look like a bit much at first glance, but it's really just the logic we've been discussing. We're going to step through the key parts right now, so don't worry about understanding it all at once. This is the heart of our solution. We have a loop that keeps going until we've found the n numbers we need. Inside we have our root number, which we call I, that starts at 1 and goes up. In each pass of the loop, we first create the odd-length palindrome from I. We convert I to a string, and then do that trick we talked about to build the palindrome. Then, we do the same thing to create the even-length palindrome from that same root I. So for each root number we're actually creating two candidates to test. So once we have a palindrome like our odd length number, what do? We have to run it through our second test. We have a little helper function, let's call it to base k friends, that takes our number and converts it into the target base, k friends. This is a standard algorithm. You just keep taking the number modulo k to get the last digit, then divide by k and repeat until the number is 0. After we get the string in the new base, we pass it to another simple helper, check, which just sees if the string is equal to its reverse. If it is, bingo, we've found a k-mirror number. We add it to our running total and increase our counter of numbers found. So how much better is this approach? It's night and day. The time it takes to run is no longer tied to the gigantic size of the final answer. Instead, it's just related to how much work it takes to find n valid numbers. Since we're generating candidates so efficiently, this is very fast. For memory, or space complexity, we're also in great shape. The only significant extra memory we use is to temporarily store the digits of a number when we convert it to base k preds. The number of digits grows logarithmically with the number, so this is very small. We describe this as big O of log m spreads, where m is the number we're converting. So to wrap it all up, what are the big ideas here? First, if a problem involves searching through a massive range of numbers, the simple brute force approach of checking every single one is probably a trap. It's too slow. The breakthrough for this problem was to flip the script. Instead of checking, we generate. We built a machine that only produces numbers that are already base 10 palindromes. This drastically cut down our work. And finally, we saw a neat trick for generating all palindromes by constructing them from a simple, incrementing root number. This kind of thinking, from checking to generating, is a super powerful tool to have in your problem-solving toolbox. And that's it. I hope this breakdown made the problem feel a lot more approachable. If this video helped you out, I'd really appreciate it if you hit the like button, and maybe subscribe for more explanations like this. If you have any questions or a different way of looking at it, drop a comment below. I love reading them. Thanks for watching, keep up the great work, and I'll see you in the next one.